Hello viewers, welcome back to another section of my tutorial videos. In this video, I'm going to take you through limitations of naive Gaussian elimination. In our previous video, we went through the principles of naive Gaussian elimination, then we took an example, then we solved. So if this is the first time you are coming to this channel, please like, you subscribe, and you share this video, and make sure you turn on the notification button so that when I post any new video, you'll be able to get it. So in this video, as I said, limitations of naive Gaussian elimination. So you saw that in the naive Gaussian elimination in our previous video, we dealt with two main principles. Okay, let me say theory, because when you are given systems of equations to solve, you first convert them to the matrix form. From the matrix form, you make sure that you use the forward elimination of unknowns, then you use your back substitution to get your solutions. So now, what are the limitations of the naive? What can the naive method use to be solved? So the first one we're going to talk about is the runoff errors. Now when we talk about runoff errors, because the naive Gaussian elimination deals with subtraction and additions and all that, you see, we tend to subtract and modify row entries and subtract to eliminate other entries. So because of these subtractions, the effect is that we tend to use different decimal places, which when you omit one, it affects the final answer. So let's see, assuming you get 2.456, so let's say 2.45, then maybe 6 7 as one solution after maybe simplification, then you get another 3.428914. You see, when you are dealing with simplifications or when you're dealing with numbers, you choose a uniform significant numbers, so that all that you'll be doing will have a uniform or decimal places and significant numbers. So in this case, when we take our decimal significant numbers to be, let's say, 5, so 1 1 2 3 4 5, here to make it 1 2 3 4 5, omitting these two, and we've just omitted it in our subtraction or in our division or in our multiplication, but it will at long run affect the final answer. So there is one limitation of the Gaussian elimination method. Now when we say division by 0, for the elimination, I told you we focus on the first entries. We have the A11, A21, then we have the A31 for 3 by 3 matrix and different for 4 by 4. When you are supposed to eliminate this, you make sure you divide this by itself and multiply it by this, so that you can come and subtract the solution from this. But a case where you get entries where you want to eliminate, and before you can go ahead with your elimination, you realize that maybe you've done your first elimination, you have 2 5 4 here, maybe 2 5, then you have 4 somewhere. What will happen is that, assume you have 0, then you have another 0 here, then you have, let's say, 3, then you have 0, then maybe 4 5. So see this situation. In a situation like this, you have to eliminate the 4. Always the last eliminated row should be the last one. You should have 2 of them omitted, so that you can find the last, or you can find only one unknown. But in this case, this place that we need to modify to get 4, it's already 0. There's no way you can modify 0 to get 4 and subtract. so that here too be 0. For that reason, naive Gaussian elimination cannot work in this situation. Take note. So division by 0 is another limitation of Gaussian elimination, and this is a short video I made on the limitations of naive. One will ask, why do we use different principles to solve systems of equation in numerical analysis? It's because limitations of one step will help emerge a new step at the other. Now, we have a way of correcting all these limitations, and that is going to be the Gaussian elimination with pivoting. I hope seeing you in the next video, because you are going to be doing pivoting, that is Gaussian elimination with pivoting. Kindly subscribe, you turn on your notification button, then you share to your friends to also help them. Thank you.